Welcome to our third morning. I'm very happy to introduce our next speaker is Angelo Lopez, and he will speak on what you read there, Ulrich bundles and relation with complete intersections. Please.
Thanks a lot. I certainly won the contest of the longest title of this conference. So, of course, many thanks to organizers, because this place is wonderful, Rio is wonderful, and I come back here always with a lot of pleasure. But my thanks really go to Fernando, because yesterday I was thinking, what should I say about Fernando? And then the first word that came to me is a friend. Fernando, of course, is a very good mathematician, and I appreciate that a lot. But when I think about him, I think more about him as a friend. And that's not, it's not something that I can say about many people. Unfortunately, probably it's because of me, but in any case. So I want people to know something about how important Fernando was in my career. So we were graduate students together in Brown. He's my mathematical brother. But probably a lot of people don't know that we used to live in the same building. It was a small, one of these New England houses, 3-story house. I was living in the third floor, and Fernando was living in the bottom floor. And what I did many times at night, late at night, Italian way, like 3 a.m., something like this. I will go downstairs, and Fernando was still awake. And then we'll start discussing mathematics, and it was incredible because I learned so much from him. When I arrived there, I thought I knew algebraic geometry. I had already studied for a couple of years. But talking to Fernando, I realized that I knew nothing. And he explained to me so many things. It was very, very important for my growth. As a graduate student and then as a mathematician. So thanks again. And now I'm going to speak about Ulrich bundles. So I will make a brief introduction. So the goal here is to study vector bundles on a given variety. But not just a variety embedded, so with a fixed embedding, a variety embedded in Pn. Okay? So in the literature, of course, there is a lot of literature about study of vector bundles, but I want to point out two sides. The first one is the study of vector bundles without intermediate cohomology, which are called arithmetically co-Macaulay bundles. So a vector bundle E on X is arithmetically co-Macaulay if all the intermediate cohomology vanish and all the twists also. So hi of E of j is 0. Or let me set here n for the dimension of X. And let me assume for the rest of the talk that X is smooth. It's not important that it's over the complex numbers, but probably I will think about this in this case. So arithmetically co-Macaulay means that the intermediate cohomology vanishes. So this is for 1 less than or equal I less than or equal m minus 1, and for every j. Okay, so there is a lot of work in this subject. Maybe the first time these things came out is Ulrich's theorem, which says that if you have an ACM vector bundle on Pn, then it splits as a direct sum of line bundles. So this is one side. Another side is the generosity loci. Of course, the generosity loci do not need the embedding, okay? But let me just put it loosely that you study a vector bundle through the geometry of the generosity loci, and if you have an embedding, then, well, okay, maybe it is the generosity loci also have some projective properties. And just to make a name here. One of the main contributions is the famous Arch-on-cell correspondence. Okay, that says that under given conditions, there is a one-to-one correspondence between vector bundles and codimension to subvarieties. Okay? So what I'm going to talk about today is a combination of these two things. And this is in the special class of Ulrich vector bundles I will now define. So a rank R vector bundle E on X is said to be Ulrich if it satisfies one of the following equivalent three conditions. Okay, so one is just E seen as a sheaf on Pn as a linear free resolution of length the codimension. Okay, so you see E as a sheaf on Pn, and then you have a linear free resolution of this type. So it's a linear free resolution, and the length is the codimension. And these Betti numbers are known. Okay, I'm not going to write the formula. They are binomial coefficients or something like that. I don't remember exactly. But the Betti numbers are known. So this is one possible condition. The second condition, which is the one I like the most because I like to play with cohomology, is this. Yeah, I wrote dots, but they disappeared. Thank you. The second condition is vanishing of this cohomology group. So now this is for every I. So even I equals 0. This is very important. But on the other hand, P is only between 1 and the dimension of X. Okay, so some bundle that satisfies some cohomology vanishing, which are is not clear here, but which are actually stronger than this, meaning that Ulrich bundles are arithmetically con Macaulay. It's not clear here, but you can prove it, for example, with the resolution. And now the third one is this: if pi from X to Pn is a finite projection, is a finite linear projection, then the push forward is trivial. Okay? So these three conditions are equivalent. This was proved by Eisenbach and Schreier at some point in 2000, more or less. Okay, a little bit of history of Ulrich bundles. So first of all, they were born not in algebraic geometry, they were born in commutative algebra. People in the 80s studied some special modules over the polynomial ring, which are called maximal Cohen-Macaulay modules. I don't know very much about this side, so hopefully I will not say anything wrong, but in any case, people study these modules, and as it turns out, the sheafification of these modules is an Ulrich bundle and vice versa. If you take an Ulrich bundle and take the associated module, then it's a maximal Cohen-Macaulay module. So for many years, this subject, was done only by people in commutative algebra. In 2000, there is a main paper of Eisenbach and Schreier that brought this into algebraic geometry. And they, first of all, they proved this equivalence. And then, well, they proved several things. But also they showed in subsequent papers why Ulrich bundles are important, because one may say, okay, why do I care that a variety has a bundle that satisfies all this cohomology vanishing? Well, Ulrich bundles are important for many reasons I don't have time to explain, but I will say two of them. The first one that was proved by, both of these were proved by Eisenbach and Schreier. The first one is that if a variety has an Ulrich bundle, then the Chow form of the variety, the Chow form is the divisor of the hyperplanes of codimension n+1 that meet X. So it's a divisor in the Grassmannian. Well, if a variety has an Ulrich bundle, then the Chow form has a very specific, a very special form. It's the determinant of a matrix of linear forms in the Plücker coordinates. Okay? So it's very, very special. And the second one, which is, I think, even more important, is that, I will say this very loosely. So you have this variety X embedded in Pn. Consider all the possible coherent sheaves and all on their cohomology of the twists. So you get a bunch of numbers. Okay? You put together all these numbers in a Q vector space, a bunch of integers, right? Hi of Ej. Okay? So you get a bunch of integers. You put all these integers in a big Q projective space, and then you take positive linear combinations of this set, elements of this set. This is called the cone of cohomology tables. Okay? So with all the cohomology of all possible coherent sheaves on X, you form a cone in a certain infinite dimensional vector space over Q. And the theorem that Eisenbach-Schreier proved is that a variety has an Ulrich bundle if and only if the cone of cohomology tables is the same as Pn. Is the same cone as the one of Pn. Okay? This is very strong. In a way, it reminds me of Artian conjecture, right? When people prove that variety of small codimension have the same cohomology of Pn. It's kind of similar. In any case, so I think from this point of view, it's already clear it's important. On the other hand, we don't know if there are Ulrich bundles or not. In fact, this is a conjecture. This conjecture is of Eisenbach and Schreier and says that any X in Pn carries an Ulrich bundle. Now it's 24 years, so this conjecture came out. It came in 2000. And I think it's stuck, because the only case where we know the conjecture is for curves. For curves, it's actually easy. It's an exercise. But for surfaces, for example, we don't know if every surface has an Ulrich bundle. Higher dimension, the situation is even worse. Of course, there are many cases, many results that have been proved. I will mention some of them. But in this generality, there is not much is known. Okay? So how to link this to the second? So how to link this to the second subject, which is the genera loci? Okay, so my idea when I started to study Ulrich bundles is that, first of all, they are positive. I mean, here you see that they are globally generated. But in fact, they have a lot more positivity than what sits in here. I don't have time to explain this, but for example, most of the time they are ample. Actually, sorry, most of the time they are very ample, which means the tautological is very ample. Okay? So they have a lot of positivity. And my idea was, okay, since they are so positive, then this positivity should be reflected in the degeneracy loci in some way. I mean, maybe also the degeneracy loci have some positivity properties. So I started to investigate this. And the idea was to try to understand what is the relation with subvarieties. And in order to state this, I have to start some notation. So relation with subvarieties. So, okay, so let me start some notation. So suppose that you have a subvariety Z containing X of pure codimension 2, and I think I want to assume it also Cohen-Macaulay. Okay? And suppose we have also a divisor on X, which, by the way, soon will be the first chain class of the bundle. Okay? And this will be the second chain class. But in any case, for now, Z is a subvariety and D is a divisor. Then you have this exact sequence. And from this exact sequence, you get a map which goes from here, hn minus 2 kx plus d restricted to z, and then you go to hn minus 1 of the ideal sheaf of z in x twisted by kx plus d. I'm going to call this map gamma zd. Okay? Dualize this map, and you get this. So the dual of that is actually x1, or x of izx of d, or x. So you see that here extensions are appearing, so there is a bundle here somewhere, right? Or at least a sheaf. And then this is going to be to the third dual of this, which is H0 omega z of minus kx minus d. Okay? So we have this map. Given this pair z and d, we have this map. Okay, so here's the theorem we proved, given this notation. By the way, this theorem was proved by Ciliberto, Flamini, Knudsen for n equal 3. But the theorem is for any n. So the theorem says the following. So the idea is, what is the relation between Z and E? Can we give a Harshon-Serre correspondence for Ulrich bundles? The answer is yes, and this is what I'm going to write. Of course, it's a lot more complicated. It's not as beautiful as Harshon-Serre correspondence. Nevertheless, I think I will show you that it can become beautiful if you pay enough, attention. Okay, so let X in Pn be smooth of dimension. I'm going to assume n at least 2, and degree also d at least 2. By the way, I did not mention any example of Ulrich bundles, but for example, if you take Pn and take O of 1, then the trivial bundle is an Ulrich bundle. Okay, that's the first example. And that's why there I want to put d at least 2, because if I put d equal 1, then there is only the trivial bundle and it's not interesting. Okay, so we have this, and then we have a divisor. Okay, then the theorem says the following. X carries an Ulrich bundle E if and only if, that's important, if and only if there exists a subvariety Z containing X, which can be a subvariety such that, so it has a lot of properties. Hopefully I can fit them here. So first of all, this can be empty. I mean, it's very rare, but it can be empty. Either Z is empty or pure codimension 2. B, so if Z is non-empty, and then Z is smooth, it can be disconnected also. For example, if n equal 2 is zero dimensional, so it's disconnected. In many cases not. In many cases actually reducible, but in any case. Okay, then Z is smooth if, Ulrich bundle of rank R. Sorry, or rank R with C1 of E equal D. If and only if. Okay, so we're fixing the rank in the first chain class. So if Z is non-empty, then Z is smooth if R equal 2 or n less than or equal 5, while if n at least 6, then Z is reduced. Cohen-Macaulay, and the singular locus and the if singular, it can be smooth. So either smooth or singular locus as dimension n minus 6. So these are the properties of Z. But there is something else. So there exists Z as a variety, and also there exists a subvector space W containing this x1 of dimension R minus 1 such that okay, I will write this such that the following conditions hold. Okay, so such that I, if Z is non-empty, then, so this is the map that I just erased. So let me just rewrite this map. Maybe here. Okay? So if Z is non-empty, then this is what? This is a sublinear system of this, right? Generates. It's base point free. It's base point free. This is very important, because this is going to say that this subvariety Z has some base point free linear series, and so has a map into a projective space, and it gives a lot of information on Z. I don't have time to explain this in detail, but what I'm going to tell you is that in the theorems we prove this condition is very important. Okay, then there are several other conditions too. You have this vanishing, H0 kx plus nh minus d is 0. Then we have more vanishings. Okay, so H0. So this actually doesn't involve z. Okay, so x has to satisfy this, period. xd has to satisfy this. H is the hyperplane divisor. Okay? Okay, 3, H0 Iz in X of D minus H is 0. This is a property of Z. 4, there are 6 of them. So 4, if n is at least 3, then we have more vanishings. Hi of Iz on X of D minus PH. This is 0 for 1 less than or equal I less than or equal n minus 2, and 1 less than or equal P less than or equal n. 5. Okay, and this is a numerical condition. Again, I don't have time to explain this, but Ulrich bundles have a very, very strong numerology. And the reason is very simple. The reason is because of these vanishings. Once you have this vanishing, all the Euler characteristics of this guy have to be 0, because all the Hi vanish. So the Euler characteristic is 0. If you translate this into Riemann Roch, it gives many conditions, gives actually n conditions on the Chern classes. Okay? And these numerical conditions are kind of hidden in this definition, but they play an important role in the study of Ulrich bundles. And to my point of view, this is probably the main obstacle to construct them. Because you not only have to construct a vector bundle that satisfies some properties, but the numerology has to be perfect, otherwise it doesn't work. Okay? And the numerology is hidden in this Euler characteristics. So in any case, here we have another one, which is this, minus 1 to the n minus 1 Ki z in X, again, D minus PH. This has to be equal to R minus 1 chi of Kx plus PH. This doesn't depend on Z, of course. Again, for 1 less than or equal P less than or equal N. So this is saying that the ideal sheaf of Z has to have a certain Euler characteristic with these twists, has to have a certain Euler characteristic which is given simply by X and embedding. Okay? And finally, 6, I don't have time to explain what is this map, but we have a map H n minus 1 of I Z in X of D minus NH. We have a map that is cooked in the same way I took the gamma, in a similar way. This goes to W dual. Here we have this W that doesn't appear very much. Okay? This W here. I mean, the way I think of this is this is a linear series on Z. Okay? A base point free linear series on Z. It's not very precise because actually the base point free linear series is this one. But often they are the same. In any case. So you have this W, and then you have a map here, tensor Hn of Ox of minus Nh, cooked in the same way, and this map is either injective or surjective. Okay, well, it's a theorem, but it's very messy. I think the important conditions are this and this. In fact, my experience is that in many cases, you can reduce to these two conditions. In general, no, I don't know. But I want to show you that if you specify X, then this very complicated thing can become very simple. And sometimes you get a lot of information, maybe also the one that you needed. Okay, so for example, let me show you a corollary. So corollary 1. Okay, let's take X a hypersurface. Okay? So let X in Pm plus 1 be a hypersurface of degree D. D always at least 2. Okay? So now this is a very simple case. And what is this Z? Oh, by the way, a variety Z that satisfies all these conditions, I called it a Ulrich subvariety, simply because it's a variety that gives an Ulrich bundle. In fact, it's not about only Z, but it's about the pair ZW. Okay, but to simplify, I just say it's an Ulrich subvariety. So what is an Ulrich subvariety in this case? So again, here n is at least 2. In the case n equal 2, I also need to assume that peak x is isomorphic to Z generated by the hyperplane, which of course you know. By Nether-Lefschetz, this is true if x is very general, while by Lefschetz, if n is at least 3, this is automatic. Okay, so then x carries a rank 2. So now I specify, I just want to give a sample application. So let's go to rank 2, which should be the easier case. By the way, Ulrich line bundles almost never exist. They are very, very rare. For example, hypersurfaces don't have Ulrich line bundles. So the first thing that you ask is whether there is a rank 2 Ulrich bundle. Okay? And here is the point. X carry a rank 2 Ulrich bundle if and only if there exists a Z containing X, pure codimension 2. So in this case, it's non-empty. Pure codimension 2, arithmetically Cohen-Macaulay, no, arithmetically Gorenstein subvariety. So this means that it is arithmetically Cohen-Macaulay and that the canonical bundle is a multiple of the hyperplane. Okay? Arithmetically Gorenstein subvariety with resolution, and this is the point. So the resolution is very, so we are in Pn, and then the resolution is this, is OPn plus 1 minus D plus 1, direct sum 2D minus 1. Then we have OPn plus 1 minus D, again direct sum 2D minus 1. And then we have OPn plus 1 minus 2D plus 1. It has to have this resolution. Okay? So you see, I mean, you know, there were many conditions. Actually, here W doesn't play a role. And the reason is that W is one-dimensional, so basically it's easy to construct. And so rank 2 Ulrich bundle on a hypersurface is just a arithmetically Gorenstein. Actually, arithmetically Gorenstein follows from the resolution. You can just say if it has a subvariety has this resolution. Okay?
Where does Z come from?
D is the degree. Okay? D is the degree of the hypersurface.
No, the Z.
Z. Z is the degeneracy locus of R-1 general sections. Is the C2. The degeneracy locus that represents the C2. In the theorem. And D again, but capital D? Capital D in this case doesn't play any role because the Picard group is Z. So the C1, well, I guess I should have said that, but if you have an Ulrich bundle, C1 of E times H to the n minus 1, this is R over 2 kx plus m plus 1 h times h to the n minus 1. This formula is always true, and it's one of these formulas that I was mentioning before on the Chern classes. Okay? This is always true. Now, since C1 is a multiple of H, here you deduce immediately that D doesn't play any role. Okay? Okay, so this is a sample corollary. This is not new. I mean, maybe in this explicit form is new, But more or less this was known. And in fact, people that work with arithmetically Macaulay bundles, certainly they encounter things of this type. On the other hand, I'm going to show you now that just with this, we can prove things about Ulrich bundles on hypersurfaces. So corollary 2. So x in Pn plus 1 hypersurface of degree d okay, and let me assume then x does not carry a rank 2 bundle, Ulrich bundle, sorry, if one of the following conditions is satisfied. 1, so n equal 2, d is at least 16, and x is very general in the Nether-Lefschetz sense. So this is a surface in P3, okay? A very general surface in P3 of degree at least 15 does not carry rank 2 Ulrich bundles. 2, n equal 3, d at least 6, and x is general, because it's a threefold in P4. 3, n equal 4, d at least 3, and again x general, and 4, n at least 5. So any hypersurface of dimension at least 5 does not have Ulrich bundles. I want to say a couple of things about this corollary. Again, this is not new. All these results were known, and by the way, they are sharp. If you lower the degree by 1, there are Ulrich bundles for rank 2. I did not prove this. This was proved by several people. Maybe the names that I should put here are Boville, Kumar, Rao Ravindra. So this result was proved by, these two were proved by Boville. This was proved by Kumar Rao Ravindra. And this is also Kleppe, but not Jan Kleppe, Hans Kleppe. This was proved by Hans Kleppe. Well, when Hans Kleppe stated his theorem, Ulrich bundles were not known, but then people reconsidered and they realized that. So why am I mentioning this, aside from the fact that it's a simple application of our theorem corollary, and then this is a corollary of the corollary? Why am I mentioning this? Well, first of all, because if you read the literature, there are about 6 to 7 papers that prove these things in different ways, in several different ways. This corollary follows on this in a unified proof. I have a single proof of 1 page, more or less, that puts together all this, and using the corollary or the theorem, if you prefer, proves this. So this is powerful from my point of view, because many results were proved with different techniques. Sometimes I don't even understand them. Very deep vector bundle techniques, especially these guys here. From the geometrical point of view, it follows very easily by a computation on Hilbert schemes, basically. And of course, together with this. So from my point of view, it's powerful. Now, since in every talk, one should give at least 1 proof. No, okay, let me see. 48. Ah, no, 40. Okay. Okay, fine. Since in every talk, one should give at least 1 proof, I'm going to prove you this. Okay? The case n at least 5. The proof is 1 line. The proof is 1 line. I guarantee it's 1 line. So again, I think this is very powerful. So what happens in this case? Well, if you look at the resolution here, this Z, suppose that there is a rank 2 Ulrich bundle, okay? Then there is a Z with this resolution. And then if you look at the resolution, you realize that the ideal sheaf of Z twisted by D is globally generated, okay? If E Ulrich exists, then Z exists, and then the ideal sheaf of Z in Pn twisted by D is globally generated. Okay? Simply because here you twist. But now there is a well-known theorem of Otwinowska-Saito that says that, well, actually, 2 lines. There is a well-known theorem of Otwinowska-Saito that says that the dimension of Z has to be less than or equal n over 2, the dimension of x divided by 2. This is a famous Whitney range. Okay? And then here you get n at most 4. This is n minus 2, and so you get n at most 4. So you get a contradiction if n is at least 5. When I showed this to some people in commutative algebra, they were very surprised. Anyway, because it's very quick. I mean, okay, so this is what happens for hypersurfaces. By the way, hypersurfaces always have Ulrich bundles, but of very high rank. The rank is basically exponential on the, I think actually kind of double exponential on the degree, something like this. So this is the other end of the spectrum. For high rank, there are. For low rank, in this case rank 2, there are not. Okay? This fact that hypersurfaces have Ulrich bundle of high rank was actually proved by people in commutative algebra in the 80s. Ulrich himself, Herzog, and Bakelin. And actually, they proved more. They proved that every complete intersection, not only hypersurface, every complete intersection in Pn has an Ulrich bundle of very high rank. Okay? Okay, so let me go to the other side of the spectrum for complete intersections. So again, this is another corollary of this theorem. So here is what we proved. So let X in Pn plus C be a complete intersection of type, say, D1, DC. So it's codimension C, dimension n. Okay? Where, of course, these guys are at least 2. Okay? Okay. So what does the theorem say? The theorem says that now suppose that you will see something similar to that. So suppose that either n is at least 5. But this is by the way, there is a big difference between n at least 4 and n less than or equal 3. Varieties with dimension at most 3 often carry Ulrich bundles of low rank. But when you go to higher dimension, my feeling is that they are very difficult to find. Okay, in any case, here I'm assuming n at least 5, or B, n is 4, and X is general. And also I need to assume that it's different from 2, 2, the complete intersection of 2 quadrics in P6. Okay, so let me assume this. Then the claim is that then X does not carry Ulrich bundles of rank are at most 3. So the minimal rank of a Ulrich bundle on a complete intersection is 4, the possible minimal rank. By the way, this is called the Ulrich complexity of any variety X, is the minimum of R at least 1 such that there exists E Ulrich of rank R, which of course could be, this could be empty, okay, but if non-empty, then you take this, and this is called the Ulrich complexity of X. And now this result proves that for a complete intersection, proves that the Ulrich complexity of a complete intersection is at least 4. So this justifies the word in the title. Now, I'm almost done. I don't have time to explain a lot. Oh, sorry. There is an exception. Ulrich bundle rank are at most 3, except for X a quadric of dimension 4, a quadric in P5. Ulrich bundles on quadrics are the so-called spinor bundles. This theory is very well known. In particular, a quadric in P5 has a rank 2 Ulrich bundle, so this needs to be excluded. And also this case needs to be excluded because, again, complete intersection of type 2-2, this was proven by Eisenbach and Schreier, they do carry Ulrich bundles of rank 2. Okay, so these 2 cases are actually necessary to be to exclude. I just want to say a couple of words about the proof of this. The proof of this is very complicated because now we're dealing with complete intersections. So the numerology gets really very, very complicated. But the idea is very simple. The idea is that you take an Ulrich subvariety, which is assured by the theorem, and then you compute the Euler Z, right? And then you compute the Euler characteristic of Z in 2 different ways. One, you use the resolution, and another one, you use Riemann-Roch. You compute the Euler characteristic in 2 different ways, and then you prove that these 2 guys do not coincide. If the rank, this is incredible. If the rank is at most 3, they do not coincide. If the rank is 4, they coincide. So in rank 4, I don't know. Okay? But if rank is most 3, you get a contradiction. So this means that the subvariety doesn't exist, so the Ulrich bundle doesn't exist. It's a lot of computations, but the idea is this. But I want to point out that this idea is kind of really geometrical in the sense that now we are dealing with geometry. We consider a suitable subvariety, and we want to prove, does it exist or not on X? Okay? This is a geometrical question, and it's very different from what people did before, because before, for example, in rank 2, they were basically, they were not doing this way, but they were basically using commutative algebra, because it turns out that if, for example, a hypersurface has a rank 2 Ulrich bundle, then it's Pfaffian. Okay? So the equation of the hypersurface is the square of a determinant of matrix of linear forms. Okay, it's Pfaffian. Sorry, the square of the equation of the hypersurface is the square root of the determinant of matrix of linear forms. So for hypersurfaces, these people exploited the geometry of Pfaffian hypersurfaces. But they could not prove results of this type because for complete intersections, there is no Pfaffian stuff, basically. And the algebra gets very complicated. And also, maybe for R equal 2, something can be done, but certainly not for R equal 3, as far as I know, at least. Okay, so I think this is really new. Okay, thank you.
Thank you, Angelo. Do you have any questions for him? Yeah.
So I don't know if you mentioned that, but are there known smooth varieties which don't have rank Ulrich bundles of any rank?
No, this is open. It's open. It's
okay,
not known.
There's no single example of...
The conjecture for dimension, at least from surfaces on, is open.
Okay. And another thing that I wanted to mention is that, I mean, both of these results, they are negative, right? They do not carry to find positive results? Is it
I'm
much more
working on the
difficult?
other side now.
Oh, okay, okay.
For example, one thing that can be done is for Veronese varieties. You take Pn, but instead of taking O of 1, you take O of 2 or 3. And then you get interesting stuff, because, I don't know, for example, you take P4, and you take 2 Veronese of P4, then an Ulrich subvariety is a surface in P4. So surfaces in P4, you know, the geometry of surfaces in P4 is very well restricted.
Right, right.
I'm working on that.
Okay.
Any other questions? Yes.
So Angelo, I don't know if you mentioned, what is the Ulrich complexity of a curve?
Of the curve is 1.
1. Okay.
A curve always carries an Ulrich line bundle, and why don't I explain it? Thank you for asking, so I take the opportunity to explain it. It's very simple, because if you have a curve of genus G, then you take a line bundle with no cohomology, general. So this has no cohomology because as degree G minus 1 is not effective, so it has no cohomology by Riemann-Roch. So HI is 0, right? So HI of M is 0 for I 0, 1. And then you take E, M plus H. Now, once you remove H, you get M, and this has no cohomology. And in dimension 1, it's only P has to be the only possibility for P between 1 and N, so P is 1. So this proves that for curves there are always Ulrich line bundles. And now, since there are Ulrich line bundles, and since the direct sum of 2 Ulrich is Ulrich, then there are Ulrich bundles of any rank on curves. So here the problem is basically easy. I should say that for surfaces also there is a beautiful result that proves that not every surface has an Ulrich bundle, but if you pick any surface and a polarization that is sufficiently ample, then it has a Ulrich bundle. This is a result of Koskun with Zenga. So that's very close to prove that any surface has an Ulrich bundle. Higher dimension.
And does the conjecture predict the Ulrich complexity or not?
No. There is a conjecture on Ulrich complexity of complete intersections. Of hypersurfaces. Conjecture of Buchweiss, Heisenbach, and Schreier, which is something like 2 to the m minus 1 over 2, which is, by the way, the rank of the spinor bundles. So it's conjectured that that's the lowest possible rank of any hypersurface of dimension n. But I don't know. Also, this conjecture is pretty old.
Any more questions?
Just a curiosity about cubic threefold and cubic fourfold. Is there precise result?
They have. I think the Ulrich complexity of a cubic threefold is 6, if I remember correctly. There are some papers on this. Yeah, Faenzi and school. Yeah, exactly. I don't remember, but I think it's 6.
There is some example of stable Ulrich.
Good point. Thank you for this. So actually, Ulrich bundles are always semi-stable. Okay. Every Ulrich bundle is semi-stable. This was proved by Arshon and Casanellas. And many times they're stable, actually. So in fact, they form an open, possibly empty, but an open set on the moduli space. So they are generic in some sense, but we don't know if they exist.
Okay, thank you. Another question: your motivation, as you said, it's a Hutchon series correspondence between codimension 2 subvarieties and the vector bundles, and that makes sense to say reflexive Ulrich bundle by thinking about such a
absolutely. Yeah, it
Hutchonical
makes sense actually to talk about Ulrich sheaves, coherent Ulrich sheaves on any variety that's not necessarily smooth, as long as it's projective. And this is also a conjecture. In fact, the stronger conjecture is that any projective scheme carries an Ulrich sheaf. But I mean, you know, I stated in the smooth case because that's already open, right? So.
Are there examples on Grassmannians?
Grassmannians always have Ulrich bundles of very high rank also. They are like tensor product of Schur bundles. This was proved by Costa and Miro-Reusch. Of course, on the Grassmannian, on the other hand, it's not known what is the Ulrich complexity of a Grassmannian. These have very, very high rank again, but the Ulrich complexity of the Grassmannian is not known.
You're done? Okay, thank you very, very much.